I'm so excited. Every month, this is the best 10 minutes of my life. I have a lot of kids, and they're a lot of work. Anyway, who am I? My name is Greg Matthews. I'm an associate professor of statistics at Loyola. And what am I doing here? What I like to do is I like to take the theme of the show, and I like to do something statistical with it. Usually the theme is something like physics or material science or one of these fun sciences. Today, the theme is actually statistics. So I'm going to talk about a specific aspect of statistics. I'm going to talk to you today about Bayesian statistics, everyone's favorite type of statistics. Well, a few of you like Bayesian statistics. So who's Bayesian statistics named after? It's named after the Reverend Thomas Bayes, and there he is in his awesome outfit. It's a good Halloween costume. Okay, so I'm going to explain what Bayesian statistics is to you using a fun example that I use with elementary school students, Russian roulette. so good start, right? So let's think about the example I'm going to use here is that imagine there is a gun, and that gun is going to be used in a game of Russian roulette. And the gun has been loaded by someone you don't know, and they were able to put in however many bullets they want to put into this. Okay? We're going to let P be the percentage of chambers that are filled, X is going to be the number of times discharged, and N is equal to the number of trials. In regular statistics, frequentist statistics, we have to look at only the data. But in Bayesian statistics, you have subjective prior beliefs. Before any data is collected, you have some belief, right? And so we can use this in Bayesian statistics where we can't use it in frequentist statistics. And you're probably like, well, what does that look like? Let me give you an example. How would your beliefs differ if these three different people you knew loaded the gun? Malala versus Hitler versus Kanye. Okay? So you already probably have some beliefs about how many bullets they would have loaded into the chamber. And this is what we call a prior distribution. This is the Malala prior, and you can see here where it's high. On the x-axis here we have P, and it's we have a lot of high density near zero because Malala probably didn't put any bullets into the gun. Just a feeling I have, that's my subjective belief. This is the prior. I'm going to show a posterior distribution once we're going to run an experiment here. We're going to let x be 0 and n be 1. That means I put the gun to my head, I fired, and it didn't explode. So we're going to let x be 0 and n be 1. Side note here, if n is 1 and x is 1, and I shoot myself in the head, there's no need to do the computation anymore, I've shot myself in the head, right? So we're only going to use 0 here. So after I do that, I combine that prior with the data, and I get a posterior distribution in blue that looks very similar, because my belief and what I observed, they're about the same thing, and so I'm not updating my beliefs very much. The Hitler prior looks like this, because he's probably loading the gun, because, I don't know if you heard, Hitler, kind of a bad dude, right? So this is my Hitler prior. I put the gun to my head, I pull the trigger, it doesn't go off. I combine that with my prior, and look at this posterior is moved slightly away from 1. It's moving towards 5.5 because I've collected data, I've updated my beliefs. This is how we live, right? We have some subjective beliefs, we collect data, and then we update after we collect the data. Unless, of course, you're a Republican and no amount of data will convince you of anything. Sick burn! Okay, this is the Kanye prior because no one has any fucking idea what he's gonna do. He can load all the bullets, he can load none of the bullets, he can put half of them in. No one has any fucking idea what Kanye is doing. I put the gun to my head, I pull the trigger, nothing goes off, x of 0, n equals 1. This is the posterior distribution. Now, I actually showed this to Kanye, and I said, what do you think about this? And he drew this right there, and I'm like, no, Kanye, no! That's why you lost that $1 billion contract with Adidas, no! And then he started screaming about DEFCON 5, and he went back to Italy with Bianca. Okay, still not wearing shoes. Okay, so recall Bayesian statistics is founded by Reverend Thomas Bayes. He lived from 1701 to 1761. We need to update this. This was a long time ago, okay? Let me upgrade you, if you will. We're going to take Bayesian statistics, and we're going to do some Bayesian statistics with an E. And this is founded, if the other one was by Reverend Thomas Bayes, this is founded by Beyonce Giselle Knowles-Carter. These are Bayesian statistics. I'm going to call these Bayesian statistics just so that we can tell the difference. So what I did is I found a data set. What are Bayesian statistics with an E? It's just statistics about Beyonce. That's all it is. But I found a data set of all of her lyrics, and there's some information about the data set right there. You can do a whole bunch of stuff with this, but the really interesting thing I found was, let's look for words that are only used on a specific album. They're only used on one album, not on any other album. Which words are used the most on each album? So these are the answers for Dangerously in Love, B-Day, Sasha Fierce. These are the ones that were used the most often on that album and never on any other album. So these are the first three. These are words from the second, fourth, fifth, and sixth albums. But what's the most recent album? She has a seventh album, Renaissance, which came out in 2022, I think. And the number one most used word in that album is yakka yakka, which was used 44 times. This is if Abby does data science for social good, I do data science for nonsense. Tagline. Yeah, that's right. Now this is an interesting word. Yakka yakka is fun, but does anyone know what the second most used word is that is not used on any other album? Boom! Whoa! Beyonce! Whoa! So I'm doing this analysis. This comes up, and I'm like, that's got to be like a typo. It's got to be like aunt or something, and someone miscoded it. So I went and found the lyrics. I thought maybe she's using a song and she's using it. So I'm now going to read the lyrics to you that this appears in it, and here it is. I'm not really going to read. Did you think I was going to read it? Did you think I was going to say it 35 times on video? You're out of your minds. I'm tenured though. Did I mention that? I could probably get away with it. Should we test the tenure? She's like, yes, test it. She's trying to get me canceled. You're going to call my dean immediately. All right. So, Beyonce, huh? Number 3 was fan. Number 4 is whoa. Yep, Beyonce. And then we have that word. I think that's thotty. I don't know what it means because I'm 41 and have 3 kids. No idea. And then she also used motherfuckers, which is, I would think, maybe at least once. Never before. Okay. So what's next? We have Reverend Thomas Bayes. We have Beysian statistics. We have Beyonce, Giselle Knowles Carter. We have Beysian statistics. What we need to do is combine them. What happens if we combine Beysian statistics with Beysian statistics? So here's what I did. I took, we're going to build a Beysian model, and we're going to predict the probability that Beyonce will win a Grammy. We're going to use some covariates here. We're going to look at the number of Grammys won by year, the number of nominations by year, and we're going to have an indicator variable. This is either a 0 or a 1, indicating whether or not she released an album in that year. And we're trying to estimate the probability that she's going to win, given that she was nominated for a Grammy. So this is the model right there, and I'm sure if you're not a smooth brain, you can read that, but since some of you here probably can't, I'm going to draw a picture for you because, well, I'm a full professor. I look down at you from the ivory tower, so I'm going to make it simple for you. So here's, got some groans over here, and that's what keeps me going. It's not the laughs, it's the groans. So here we're going to model YZ is the number of Grammys won in year Z, and Y stands for Yonsei, obviously. And we have Pi Z, which is the probability that she wins a Grammy in year Z, given that she's nominated for one. We also have NZ, which is the number of nominations in year Z. These are covariates. And we have IZ, which is the indicator variable for an album release in year Z. But in this, since it's a Beysian model, we don't really use I here. We don't use IZ for indicator variables. We use JZ for indicator variables because it's a Beysian model. And so in this schematic, the next level down, we're gonna have our parameters, and these are called child nodes. But in a Beysian model, they're not called child nodes. They're called Destiny's Child nodes. And what color should they be? They should obviously be blue because they're child nodes.
Yes.
It always takes people a while to catch on why they should be blue, but just think about it for a little bit. At the bottom here, we have our priors. These are hyperparameters, and they are parameters for the priors on alpha, beta, and gamma. Just like before we had priors, I showed you the Malala, the Hitler, and the Yeezus prior. I'm going to use non-informative priors right here. So basically my prior probability is flat, which is the Yeezus prior, so we put Kanye all the way down there. We put Kanye in all of these things. Okay? This is a schematic of this diagram that I'm going to show you. And so here, let's look at some results. This alpha, beta, and gamma parameters, I should say, alpha is a baseline probability of winning a Grammy. Beta is how the probability changes with the number of nominations. And gamma is how the probability changes with a Grammy, with an album released that year. Okay, so results. So here, these are some Bayesian, I'm saying it wrong, hold on. These are some Bayesian posterior distributions for alpha, beta, and gamma. Here's the posterior probabilities. This one's not too interesting, but you'll notice that kinase there, because in a posterior distribution, it's a combination of the likelihood and the prior, and so a little bit of the prior shows up in every one of the posterior distributions. I guess it makes more sense if you know about Bayesian statistics. So this one's not that interesting, but this one right here this is the posterior distribution of beta. And by the way, my theory is that in these concerts that Beyonce is doing, she's making these posterior distributions, because what else could she be doing there? Anyway, so if you look at, and you see this, there's a 0 right here, and most of the density of this is positive. What that means is the more that, this is some actual results here, the more Grammy nominations she's nominated for, the higher the probability of each of those she is to win. Right? So if she's nominated for 10 awards, she has something like an 80% chance to win each of those, whereas if she's only nominated for 2, she maybe only has a 40% chance to win each of those. Okay? The last result here is this gamma, and you can see that the 0 here is on this woman's face, and most of this density is negative. She's less likely to win when there is when there's an album released in that year, because usually there's a lag and she wins the year after, because people catch on and then her albums are awesome. And she runs the world. What have we learned today? Don't let Hitler load your revolver if you're going to play Russian roulette, obviously. Always remember to color your Destiny's Child notes blue. And finally, B loves the C word. Follow the show on the Instagrams and the socials. I'm Greg Matthews.